Hello everybody, I am Giuseppe Giannino from Isotta Fraschini Motori, which is an Italian company controlled by Fincantieri, a big global leader in the field of shipbuilding. And today I would like to talk to you about our usage of HDF format on board of power generators for marine and terrestrial applications. Hope you will appreciate some historical notes about Isotta Fraschini Motori. So everything starts in 19 when Cesare Isotta and brothers Vincenzo and Antonio Fraschini founded the Isotta Fraschini and Company. The company began to design and produce all the parts of vehicles on its own, and in 1904 it became Isotta Fraschini S.p.A. in Milano. For many years, Isotta Fraschini designed and produced exceptional engines for aeronautical, vehicle and naval use, both for civil and military application. In 1930s, the factory moved some of its factories to the Saronno area, and at the end of the war, however, the conversion of the company from military to civil failed, and the company was placed in liquidation. Important products were designed and manufactured in the railway, shipbuilding and industrial sector. But at the beginning of 1960s, a plant to produce highly successful diesel engines was founded in Bari, where we are now located. At the end of the 1980s, Isotta Fraschini Motori was merged with Fincantieri, as I told you in the beginning, and now it is controlled at 100%. Today in Bari, research and development production continues and is the only world headquarters of the Isotta Fraschini Motori brand. So let me spend some words about the company today. Isotta Fraschini Motori today deals with design and production of four main asset categories. We have the propulsion one, the power generator asset, the industrial engines, and the engines for special applications. About 2 years ago, Isotta Fraschini Motori has started the so-called iFuture program, which is aimed to design a new category of engines compatible with actual standards in terms of emissions, power requirements, and able to work with different fuels, also renewable. Another main goal of the iFuture program is to develop and integrating new technologies on board of power generator and so in general of engines, such as artificial intelligence and machine learning technologies and IoT systems for three main goals: improving performances, improving maintenance operation, especially when mounted in strategic location far from the headquarters, and optimizing the whole engine life. Let's consider now a typical use case, taking into account a typical application for power generation. This is a very complex scenario where lots of information travels around our asset. Usually we have two main logical modules, so the engine control unit and the automation system based on a PLC logic for auxiliary operations, such as warning, alarms, and so on. A huge amount of sensors are connected to our two main logical modules, and sensors usually are for catching information about pressures, temperatures, electrical parameters, velocity, viscosity, and so on. The two main protocols are CAN bus and Modbus. About information, so how many information how many data we could generate. So usually depending on the engine configuration, we could generate between 100 and 500 time variant variables with different sample rate. We could generate between 200 and 300 events per day. So events are logical status, Boolean information, alarms, warning, and so on. And in operative scenarios could require a power generator in working mode for 24 hours, 365 days per year. But how HDF format has helped us to reach our goal, so to satisfy our needs? So the main goal of the project was to equip the asset with a custom system for continuous data recording with the following properties. So highly reconfigurable based on power generator configuration and application, easily to integrate on new asset and already on field asset, highly reliable in terms of data storage, availability, data protection, and in data integrity, fully autonomous in terms of response to working conditions such as continuous reboot state and so on. Easily accessible and usable, so also no expert users will be able to use it on field. Capable to natively organize a huge amount of data for a ready-to-use interpretation, and also data must be correctly time-referenced. As you can see, here we have a very high-level architecture. We have two main entities, the server side and the client side. So focusing on the server side, here we have our onboard data recording installed on our asset. Running on the data recorder, we have two main processes. The first one is a Python reader process, which is in charge of sniffing data traveling around the protocols, so such as Modbus, CAN bus, and so on. And in the beginning, it just uploads two main configuration file, the parameters configuration file and the variable list file. Another second parallel Python process is the one which is in charge of initialize the HDF5 file and periodically control the HDF5 dimension. And also we have another main component and very important one, that is the web server always available, which allows the user to connect via a browser interface to the onboard data recorder to just setting it, controlling status, and of course download data. On the client side, of course, we have our user equipped with a laptop on field, so it establishes a connection with our onboard device through a wireless or a cabled connection, so it can access to the stored data and can download them, and through the interface it can also it is also able to analyze the stored data. I would like to show you now the two main HDF5 file structures. So these structures are of course related to our two main protocols, the Modbus one and the CAN bus. The first one, as you can see in the slide now, is made of a root folder on top, and then under this one we have two main group. So the first group is the timestamp group, and the second one is the Modbus variable group. Under the timestamp group, we have just one dataset where all the timestamp associated to the sample rate are stored. Inside the Modbus variable group, we have a certain number of dataset where the number of dataset is equal to the number of variables traveling around the Modbus protocol. And at each dataset, we just associate a certain number of attributes depending on the variables. So usually the attributes that we store are the unit factor, the factor, and also if there is some alarm on that variables, thanks to the threshold algorithm that runs inside the main Python process. This structure is justified by the concept that now I'm showing to you. So just consider that at each sample rate we acquire all the Modbus registers. This is the very big difference between the Modbus HDF5 structure and the CAN bus HDF5 structure, as I'm going to show you. Here you can see the HDF5 file structure associated to the CAN bus. So just consider that each CAN bus packet has a variable number of information inside. These information are called signals. Each packet travels on the bus with its own sample rate, and the data recorder must follow them and serve the correct acquisition time for a right post-analysis. So this is why the structure of the CAN bus is different from the HDF5 structure for the Modbus. So about the architecture, we have on top always our root folder, and under the root folder we have a certain number of groups. Each group is associated to a CAN bus packet. Inside the CAN bus packet we can find a certain number of dataset, where the number of the dataset is equal to the number of signals inside to the specific CAN bus packet. And of course, associated to each dataset, we find a certain number of attributes. These attributes could be the unit, the factor, the minimum value, the maximum value, and so on. And always inside each group, so inside each group associated to each CAN bus packet, we find also one dataset associated to the timestamp, where all the timestamp, so the acquisition time, are stored for the specific CAN packet. So the main programming language used for our data recorder is Python, and the library used for managing the HDF5 file is the H5Py library. How our software architecture is made. So I just would like to show you a very high level details. In the beginning, the main Python process uploads the configuration file. Inside the configuration file, we just find information about our HDF5 file, the Modbus channel, the CAN channel, and so on. After the uploading configuration file, the main Python process starts to ping the endpoint, so the PLC, the engine control unit, and so on. If the answer comes to the Python process, it's gone. At this point, it uploads the second file. The second file just has inside the variable list map. After this, the main Python process start to initialize a new HDF5 file with the parameter that it uploaded in the beginning. So if the init of the new HDF5 file is okay, it starts the reading process on the selected protocol. So for each iteration, it just sniff the data from the protocol, insert the data following the architecture that I showed to you before inside the HDF5 file. It checks if there is some alarm, so thanks to the threshold algorithm, and if there is some alarm, this is inserted as attribute inside the specific dataset, and then it checks the HDF5 file dimension. So if of course, if the dimension is higher than the one defined in the configuration file, a new file is initialized, and so on. Considering the following test conditions, we are very excited to show you benchmarking analysis. Let's consider an acquisition time range of 14 minutes with a resolution time of 1.5 seconds using a Modbus protocol on board of a power generator for industrial application. So we just acquired about 560 metrics, so time variable for each variable. So storing this data inside a txt file, we just got a file dimension of about 15 megabytes. But storing the same data inside the HDF5 file, we just got a file dimension of 831.7 kilobytes. The main page of the interface, which allowed the user to select store the data and downloading them, is here represented. So we have the login page on top left, and then we have the page through which the user can select the desired file and download it. On right, we have the page which allow the user to upload an external or an internal HDF file, selecting the variable which he wants to show, so to plot, and then of course the tool allows to visualize the data. So it upload the specific dataset and show the data to the user. Hope you have found this presentation interesting, and thanks for your time. See you next time. Bye bye.